Hi everyone, welcome to NASA's Jet Propulsion Laboratory in Southern California. I'm Raquel Villanueva and we are so excited to have you join us as we gear up for the launch of SPHEREx, which is NASA's latest mission to explore the universe. Now we will be taking your questions live and we will also show you a behind the scenes look of SPHEREx as it gets ready for launch, which is now just a few weeks away. So if you have a question you'd like to ask, you can use the hashtag AskNASA or drop them in the chat below. So before we get to your questions, let's get an up-close view of SPHEREx, and for that, I'll hand it over to Emily Richardson.
Thanks, Raquel. I'm just a couple hours north of LA right now at Vandenberg Space Force Base, where SPHEREx is going to launch in just a couple of weeks. I'm currently at the Astrotech Space Processing Facility, and I'm inside the clean room with the Space Telescope itself. This is SPHEREx, NASA's next cosmic mapmaker. And I'm joined today by Jen Rocca, Mission's Project Systems Engineer. Hey, Jen.
Hi, nice to meet you, and thanks for being here, Emily.
Yeah, thank you. So tell me a little bit about this mission, NASA's next cosmic mapmaker. What does that mean? What's SPHEREx going to do?
So SPHEREx is a really special astrophysics mission. It's going to lift off here from Vandenberg Space Force Base on launch pad number 4 atop of the Falcon 9. It will go about 650 kilometers above the surface of the Earth, approximately 400 miles. And instead of looking down at Earth, it's going to look out at space. And our mission is going to take 102 channels in the near infrared of every single pixel in the celestial sphere. That's all of the space outside of Earth. And we're making a giant map of the cosmos. So we literally are a cosmic mapper.
Yeah, that's incredible. Every pixel of the entire cosmic sphere.
Yes.
So what are we going to use that data for?
Well, we have 3 major science themes on our mission, and we've chosen the wavelength ranges of the electromagnetic spectrum that we want to observe based on the science that we want to get. So first, we're interested in cosmology, which is really about the physics of the early universe just after the Big Bang. And we're trying to take enough of the spectrum to see the physics of the universe back in time. So that's pretty exciting. It's really a part of the universe that we don't know a lot about, and so we're hoping to understand that a little bit better. Next, we've chosen some wavelengths that allow us to locate ices in the cosmos outside of our solar system, and that might be interesting for future missions of more interesting places to look where there could be water ice. And then lastly, because of our orbit, passing over the poles of the Earth more often than other parts of the Earth, we get more signal in those directions and are able to look at more dim things in the universe. That allows us to look at the beginning of galaxy formation in galaxies outside of the Milky Way, and that's pretty exciting for astronomers as well.
Sounds really exciting. And you know a lot about this mission because you've been on it since the very beginning, right? Mm-hmm. What does it mean to be a project systems engineer, and has that role changed over the last decade?
Yeah, so I started on SPHEREx back in about 2015 when it was just a proposal, and we proposed to a NASA announcement of opportunity for a competed mission to do astrophysics. And SPHEREx was selected in that proposal round. I was the lead system engineer. When we went to the next round of proposal, I became the capture lead, and my job was to win. So we did.
Congrats.
Then I became the project systems engineer on SPHEREx, and my job is to be the lead engineer for all of the engineering teams on the project and maintain an independent reporting path to the NASA chief engineer so that technical integrity is always on our mind and we make the best design possible in order to maximize the science. So that's really my job. At the beginning of the mission, I was really focused on sort of how to make the design as good as it could be for as little resource as possible. And one of the most challenging parts of SPHEREx was trying to figure out how to make the instrument cold enough to observe in the near infrared and still be safe in low Earth orbit. So we did a lot of study and design thinking at that time to figure out how to get the thermal to work and how to get the science to work. And that really was the genesis of the big shields that you see at the outside of the spacecraft.
Yeah, and speaking of that, that's definitely the most distinctive thing about SPHEREx is this cone shape. What's going on with that? Why do we need that shape?
So if you want to observe in near infrared, anything that has heat, you can see. And so when we're in low Earth orbit, we can see the sun. It's very warm at Earth, and we can see the heat of the Earth that radiates out to space at that altitude. And so we really don't want our telescope to see that. And this really design decision started with an older mission called Planck that had these radiators that were layered underneath the electronics that allowed a geometric shedding of heat. And we used that design to be the foundation of our thermal design on SPHEREx. Except in low Earth orbit, those little radiators have to be a lot bigger. And so underneath our instrument in the center of these cones, there are 3 layers of V-group radiators, and they're hexagonal structures that extend into these big conical shields. And the geometry between them is very specific so that heat photons that are generated by the electronics bounce out to space and leave our instrument very cold. It was very important for this design that they can only go in one direction, so they're always further apart as they go up, and they're in 3 layers. We actually did a test with a laser pointer to make sure that they got 7 bounces on the way out to space, and so we're really happy with the elegance of this design because it helps our instrument get all the way down to 45 Kelvin, almost as cold as you can go, without cryogenic fluid or any kind of heater, active cooler, and we do this all with passive cooling in low Earth orbit, so it's really innovative.
Yeah, that's really, really cold without any coolant.
Right.
I mean, that sounds pretty innovative to me.
Yeah.
All right, so we've had a long process to get here. We're just a couple weeks away from launch. What do we have left to do with SPHEREx to get it ready for the launch pad?
So we actually drove SPHEREx from BAE Systems in Boulder out to Vandenberg, and we unpacked her and put her on her transport cart, and then did our first functional testing where we turned on the spacecraft of the instrument, made sure we didn't damage them during shipping, and we're all finished with that now. We did our final walk down to make sure that all the bits and parts look exactly as they're supposed to, and now we're waiting for our rideshare partner Punch to get mounted on the launch vehicle. Then we'll be lifted on top of that. The launch vehicle fairing will go on, and then we'll stack on top of the rocket and lift off.
Yeah, so let's talk just a little bit about that rideshare partner. We are not the only mission in this clean room. There's another mission that actually will share the same rocket with SPHEREx. It's called Punch, and Punch will use 4 suitcase-sized satellites to study how the sun's outer atmosphere becomes solar wind. And it's sharing a rocket with us. Is that normal? Tell me a little bit about that.
So actually, when SPHEREx was first proposed, it was proposed for an announcement of opportunity that allowed us to launch on a much smaller launch vehicle. But when we came into the proposal that we actually were selected for, the launch vehicle that was selected was a Falcon 9. SPHEREx is actually small enough that you could stack 3 SPHERExes on top of each other inside the Falcon and still get off of the Earth. And so NASA saw this as an opportunity to offer a little bit of volume inside the launch vehicle for a rideshare partner. And so Punch was selected as our heliophysics brother to come ride with SPHEREx. And we're actually very complementary missions. We have very similar contamination requirements. Our instruments want to be the same kind of clean so we can process together in the clean room. They're a lot smaller than we are, so they mount on the little ring below us and don't get in the way of the photon shields. We've been together since the beginning of the design phase and have worked together to make sure that we're safe. Both of us are safe on top of the launch vehicle, and I'm really proud to offer this carpool ride to Punch on the way to space.
Yeah, and it's kind of beautiful if you think about it. Punch is going to be studying our sun, our star, and SPHEREx will be looking out in the other direction, studying billions of other stars.
Exactly, and so it's really cool that this one rocket can put up 2 missions that are going to both do incredible science.
So Jen, you told me the other day that your 25th anniversary is coming up at JPL. Congratulations.
Thank you.
What does it feel like to be at that point in your career and seeing this mission getting ready to launch?
Well, this one is very special to me because I've been on it for about 10 years. I was fortunate enough to be on the proposal, just dreaming up the first designs of SPHEREx. And now, of course, we built it, and it's really nice to see it come to fruition and be ready for launch. So I'm very excited to finally get some of that science data at first light through the telescope once we get it up into space. But I've had the experience over 25 years of working on lots of missions and seeing some of them go into space. This one's very special because it's a kind of a smaller mission than I've been on before. The team is very cohesive, and it's almost like a family. So this one is really fun because we've been in the trenches together. Our development team was together through COVID. We survived that. We recently had a bunch of our team members affected by the LA fires, and we've survived that together to continue our launch campaign. So these things draw our team together a lot closer, and I think for that reason, it's going to hold a special place in my heart forever.
Yeah, I'm so happy to hear that the team is doing okay, and
yeah,
it's just such a story of resilience, right?
Absolutely.
Yeah. Well, unfortunately, we're out of time. We got to send it back to JPL. Thanks, Jen, for spending some time with me today. It's been awesome to be in the clean room with the spacecraft, with the space telescope that's getting ready to go and be in space in just a couple of weeks. So with that, I'm going to send it back to JPL where Raquel is with another member of the SPHEREx team.
Thank you so much, Emily and Jen. And joining me now is Phil Korngut, instrument scientist for SPHEREx. Thank you so much for joining us today.
Thank you. It's a pleasure.
And can you tell the audience where we are today?
Right. So we're standing in what's called the EOMOC at JPL, which is yet another tortured acronym. It stands for the Earth Orbiting Mission Operations Center. And this is the room that we're going to talk to SPHEREx in. So all these computers behind us, they can be connected up to the ground stations, which both transmit commands to SPHEREx, but also to receive data coming down. And those are located kind of all around the globe. We predominantly use ones near the poles, in a place called Svalbard, which is like north of Norway, Alaska, and then down in Antarctica at a place called Troll.
And you know, you were saying that you are the instrument scientist that has worked on this mission for a really long time. Can you tell us how your role has changed and developed throughout the years?
Yeah, I'm so as the instrument scientist, you know, my predominant role is to understand the astrophysics measurements that we're trying to make and what makes them really hard. And ultimately, how can we build the best possible experiment to measure those and control all the difficult complications that can arise in that kind of data set? So over the years, you know, my role has changed in terms of a day-to-day. When in the early days, when we were just cooking things up, there was a lot of, you know, running calculations, turning, you know, various knobs in the design to see how, you know, different parameters that we might build would affect the ultimate measurements that we get. And then we settled on that. And then, you know, further on, as we started building things, that came together. The instrument itself came together in my laboratory at Caltech, just a few miles from here. And that's where we developed a cryogenic chamber and an optical testing facility to make sure that the instrument was well calibrated and is going to be in focus once we get onto orbit. And now we're in the EOMOC here, looking forward towards launch and operations phase, and then we're going to commission the instrument once it gets up into orbit. And after that, we start going into survey mode, and we're actually going to get that data that we're so excited to obtain. And then my role really turns into understanding how the instrument is performing in the survey and how those measurements of the instrument will impact the astrophysics measurements to make sure we get really clean extraction of the signal that we're after.
You have a lot to look forward to. Now, Jen mentioned the science goals. Can you tell us more about the types of images you'll receive and what scientists can gather from that data?
Yeah, sure. So SPHEREx is a spectrometer that also images. So if you'll bring up the first image, which is an image of our linear variable filters, or LVFs as we call them. So you can see in this image, there's three sort of rainbow pieces of glass. Those are actually pieces of sapphire, which have special coatings on them that are designed such that they only transmit a very specific wavelength of near-infrared light depending on where it lands. So wherever a source, a galaxy or a star, lands on the focal plane, so that sits right over what we call the focal plane, which houses the detectors and sits right at the core of our camera. Every position on the sky will land on every position of the focal plane, and that's how we build up this spectral data cube. If you bring up the next image, you can see kind of the resultant of a simulation here of what we're trying to extract. So in that larger image that you're looking at, that's a 1 degree patch of sky with a simulated SPHEREx observation. And every single dot and, you know, little blob that you see in that image is a star or a galaxy. Now that image at a single square degree represents 1/40,000th of the entire sky. And of course that image also, which you're looking in the larger image, is just at a single wavelength. And the power of SPHEREx is that we're sampling it at 102 wavelengths. So each one of those little thumbnails, which we're showing coming out of the center of that image, is the same part of the sky imaged at a different wavelength. So we can extract the spectrum of every little dot in that image. And the wealth of information that's just contained even in this tiny chunk is truly, truly remarkable. And, you know, we're going to have so much more than what you're looking at here.
Yeah, that image really helps put it in perspective right there. And a viewer question that we get a lot is wanting to know how SPHEREx is different from other space telescopes like Gaia, Euclid, James Webb Space Telescope, for example.
Yeah, so that's a great question, and these are all very complementary missions. For SPHEREx, if you want to bring up the next video, please. The big deal with SPHEREx is that we are industrial scale surveying the entire sky with our linear variable filter. So this animation is just showing how we build up our data cube, dithering our linear variable filter across. So the goal of SPHEREx is to survey everything, right? So it's a very broad instrument. So to compare to James Webb, which is an amazing instrument also, in operating at similar wavelengths, it's a very different kind of targeted tool. I'd like to make an analogy that's kind of like the role of a carpenter. Now, there are different types of carpenter. For instance, like a frame carpenter, a good day's work for them might be building the frame of an entire house and getting that up. But a trim carpenter might have a good day's work that's making some beautifully intricate inlays in a small part of molding or something. So in this analogy, James Webb is really the intricate molder, and SPHEREx is the large frame carpenter. And James Webb has a big old light bucket, and it has tiny pixels, so it can really resolve those details in galaxies and study individual objects. For SPHEREx, galaxies pretty much are just points. So we're trying to measure the light content in those points. You also mentioned Gaia. That's another all-sky survey, similar to SPHEREx, but what its big contribution is what we call astrometry. So Gaia was super good at measuring the precise position of really bright nearby objects, so like stars in our galaxies. And so all of these missions really provide a synergy together and help us to build up different blocks to form the final tower of our understanding of the cosmos.
Yeah, they really complement each other
They do.
there.
They do.
And I also want to know more about your role. We heard how long Jen has been here. You have been on SPHEREx for a third of your life. Can you tell us about your career path?
Yeah, I mean, I started on SPHEREx in 2012 as a young postdoc. And it's been quite a journey from there. I remember at one point, calculating that I'll be in my 40s by the time that, SPHEREx launches, and I'm, standing here at 41 and thinking about how my life has changed along with SPHEREx. And yeah, it's just amazing to see the evolution of a project. Back in the early days, it only existed in our minds. We would be in meetings discussing how to go, how we should design the mission. Then it turns into drawings that we eventually get fabricated. We cut metal, we order filters and detectors and put everything together. We test it, and now we're really, looking forward to launching it and getting the data in. And that is going to be just such an unbelievable phase for me personally, when we actually are looking through the data and just combing through that wealth of information and just get to work on our ambitious, but I think achievable science goals. And that's really ultimately going to be just so important for me.
Well, thank you so much for answering my questions, Phil. We have plenty of viewer questions that are now coming in. Okay. So to start, let's go with Daniel BRT on Instagram, who wants to know, how can we see 13.8 billion-year-old photons from the universe's start?
Yeah, so it's a great question. So the photons that we see typically from 13.8 billion years ago, that's a complementary signal called the cosmic microwave background. Those are the earliest photons that are detectable, and they come from just a few 100,000 years after the Big Bang. There are many fantastic telescopes that have designed to measure that signal. For instance, NASA's WMAP mission did that. What we're doing at SPHEREx is actually something quite different, and actually allows us to see further back, but it's not through the direct detections of photons. What we do is to make a giant cosmic map of the distribution of matter in today's universe. So galaxies are not randomly distributed. They're clumped together, and they form this big cosmic web. By surveying this cosmic web in 3 dimensions, we're able to tie that back to the initial conditions of the universe in a period called inflation, where tiny quantum fluctuations when the universe was smaller than the size of an atom have expanded to seed the overdensities and underdensities, which is where galaxies and voids form in the large-scale structure today. So it's a really amazing measurement, but we're not specifically detecting photons from the earliest measurements. We're seeing the aftermaths of the conditions at the beginning.
Thanks. Thank you so much for that clarification. And then we have Kevin on YouTube who wants to know, what are some of the more interesting questions this mission may help us answer?
Yeah, well, thanks, Kevin. And I think, our biggest three goals really, as I just mentioned, we're trying to understand those initial conditions in inflation. So that's just, it's hard for me to come up with a bigger question to answer, I think, than, what were the conditions like at the origin of the universe. And then closer to home, we're also going to survey the galactic plane of our own neighborhood for looking for water ice. So, life as we know it, of course, at least here on Earth, needs water to live. And we're actually looking for water that exists out there kind of in molecular clouds and in different phases of planetary formation. So the vast majority of water is not liquid, it's ice. And so what SPHEREx is going to do is to look through these clouds at background sources, and then we see the imprint in spectroscopy that the water ice intervening imprints on the light. So we're able to kind of get at that question of what are the conditions for the origins of life. And then our third question really is about the evolution of galaxies. When did the first stars form? How did they evolve over cosmic time? And SPHEREx gets at that by measuring what we call the extragalactic background light. So studying the diffuse glow that results from the integral of all of light production going back into the early universe.
Yeah, it's amazing to think about ices and clouds in space. We were discussing that earlier. We have another question coming in. G.I. Pugley on YouTube wants to know, what is the range of wavelengths it will image in?
Right, so we're in the near infrared, and we have 102 bands that span from 0.75 microns or 750 nanometers. That's kind of just past where your eyeball works. And then we'll go all the way up to 5 microns, which is in the transition between what we call the near infrared and the mid infrared.
Thank you. And then we have General Turan on YouTube who wants to know, how long does SPHEREx have to stay in the stable position when taking those images on all of the wavelengths?
Oh, that's a great question. And the way we set this up, so you remember the movie that I had shown, each pointing that we take is 112 seconds. So you'll take a 112-second image, and then we dither a small little slew, which lasts about 8 seconds. So you move the bore sight. This is, of course, as we're going around the Earth. We'll move it a small amount, and that puts that same part of sky on a different wavelength. Then after these little steps, we actually have to take larger steps, which can be like something like 70 degrees, to take our next set of scans, because we have to maintain the correct position with respect to the Earth and to the Sun. So as you're going around, we'll be tipping over with our cones, but we can't tip over too far, or the radiation from the Earth will warm us up. So it's 112-second exposures, and we keep going, and we'll build up that survey of the entire sky every 6 months, and our baseline mission is to do that 4 times over the course of 2 years.
And people are getting really excited for this launch. Can you let them know at home when the launch window opens?
That's right. Yeah. So we are. The launch window will open on February 27th at 7:10 p.m. plus or minus 15 seconds. So.
Well, stay tuned right around 7:09 just to be safe. So Janet on YouTube wants to know, how long do we expect the mission to last? You did touch on that earlier, but just for Janet, again, if you want to recap it.
Sure. Well, the baseline mission is for 2 years of data collection. And then after that, we've got a year where we are finally processing that to make our cosmological and water inferences. But I will add that, SPHEREx doesn't really have consumables like some spacecraft do. So it's potential to, there is potential to extend that should NASA deem that would be useful.
Okay, great. And then we have Moon to Mars Quest on X wants to know, will images and data sets be available for public access?
Absolutely, that's a great question. Thanks for that. Yes, the data that we collect on SPHEREx actually gets rolled out to the entire community basically 2 months after collection of data. So we'll take an image. We have 2 months to basically process that and to get it to a useful, calibrated purpose that would be useful for the astronomical community. And then that data is just going to roll out on a conveyor belt via NASA's URSA server that's hosted by IPAC at Caltech here. And that data will be made available to the entire public. So please have at it out there. You know, hopefully someone out there listening could find some really amazing stuff in SPHEREx data.
This is your call out from Phil. Yeah. All right, so Kevin on YouTube is asking another question. How will SPHEREx be powered?
Right, so SPHEREx is powered by a solar panel. We're in this sun-synchronous polar low Earth orbit. So basically, when we get up there, SPHEREx always keeps its back to the sun. We tip slightly off of it, but it's charged entirely from solar panels. And you know, in the orbit that we're in, which is a polar sun-synchronous orbit, basically it's always sunrise or sunset for SPHEREx. We just live on that Terminator line and a little bit, you know, off of that, but it's always a nice view from SPHEREx.
So that's positioned in a way that it will have the least light possible, correct? Since it's orbiting the Earth.
Least light possible, getting into the photon shields from the sun and the Earth. Most light possible on the solar panels, which keep us charged.
There we go, thank you. And Chromatic on YouTube wants to know, what innovations in materials or technology are being used to ensure SPHEREx can operate efficiently in space for its planned mission duration?
Yeah, that's another great question. So I would say the linear variable spectroscopy, linear variable filter spectroscopy is a great way to approach this problem. The LVFs are just a few grams of sapphire that sit right over our detectors, as opposed to other technologies which use dispersive elements like gratings or prisms. Those tend to be very massive, and that's a lot more expensive in space flight. So we've got a very efficient method of doing spectroscopy. I would also, you know, we have no propellant. We are ballistic up there. There's no consumables in that. And we have no refrigerator. We're entirely passively cooled, right? We use the actual coldness of deep space to cool down our telescope and detectors just by radiating it out and blocking the radiation that comes from the Earth and Sun. So I think I'm pretty proud of the way we've put together the mission to be useful for the community and efficient up in orbit.
Yeah, really utilizing all the elements that you'll encounter once up in space. So Karagoth444 on YouTube wants to know, how come SPHEREx can manage with a layered cone in contrast to James Webb that needs a very large sun shield?
Yeah, so also a great question. James Webb is at a different orbit than us. They're at what's called L2, which is about 1 million miles away from Earth. And you can think of that iconic James Webb, you know, the big telescope sitting on top of its sun shields. The sun shields are actually quite similar in function to what SPHEREx does, but of course, because James Webb is 1 million miles away from Earth, it doesn't have to deal with the radiation from the Earth. It also keeps those sun shields, you know, they're pointed at the sun. So if you know, those shields are like this and James Webb looks this way, and they can kind of spin any way like this to access. So it's a very similar thing, but they're in a different environment, and yeah, it's a different design to do the same purpose.
And we have a few more questions left. We have Pervel on YouTube who wants to know, can you focus it on specific wavelengths, like spend more time on a narrow band, or does it always capture its whole bandwidth?
Yeah, so there's nothing tunable, as we mentioned before. So the bandwidth of each pixel is set by that linear variable filter, which lands everywhere. So you basically are just scanning along, and whatever part of the sky lands on whatever wavelength, that's where you're sampling it. And we've designed the all-sky survey such that it's very uniform of coverage in all the wavelengths on the big sky. We will have 2 regions that are over the ecliptic poles, where because of our orbit we're able to see more often, and we'll have much deeper coverage there. So we'll have more coverage on all the wavelengths at the poles, and you know, reasonably uniform coverage around, but there's no configurable bandwidth. If you wanted to get more signal to noise, on your measurement with lower spectral resolving power, you could average those maps. The maps that I showed earlier, if you wanted to, decrease your spectral resolution, you could just take the average of a bunch of different ones, and I think that would effectively do what the question was asking. You can degrade it. You can't go above what's set by the linear variable filter.
And we have time for a couple more questions, so thank you everyone who submitted. We have one from Levi, who is a 9-year-old on Instagram, so via his adults, he wants to know, how long will it take to send back its first image?
Okay, well, great question, Levi, and thanks for asking. So the first few weeks of SPHEREx are going to be very exciting. We're going to be here in this room, and the thing is that because we're passively cooled, SPHEREx has to take some time. So it takes, after we get up there and we do the initial configurations, it'll take us about 12 days or so to get down to where we can power on the detectors, at which point we will power them on and take our first exposure, and it's going to be just so exciting to see those first images after all this time planning.
That's when the party starts. So last question is Carol on X, who wants to know what challenges were encountered during the process, and also what are you looking forward to in the months ahead?
Yeah, so yeah, we certainly had our share of challenges. I think the biggest ones, as Jen referred to earlier, I mean, we went through our design phase and all of our design reviews. In COVID, we were all in our garages and working together. That was incredibly difficult, and we had surmounted that. There were some other, we encountered technical things that we didn't anticipate. I can share one example, which is we had noticed in some of our simulations after we designed that focal plane of a stray ray, so a particular reflective path in our optics that we weren't expecting to see. And we devised a new method of making baffles inside our focal plane to prevent these glints. And it's a really fun solution that we eventually came to with something that was difficult, but there were many of those types of instances. This team has really done an amazing job, and I just want to also give credit to the amazing broad engineering and science team that SPHEREx has put together, and there are some phenomenally talented scientists and engineers working on this project.
Absolutely. And what are you looking forward to now?
Yeah, I mean, I cannot wait to see that first image and start poring over things. And then I'm just so excited in the near term to just actually see how the thing that we built, is performing, relative to its design. And, then, down the line, actually making the inferences. If we, get to be kind of the first people to make these glimpses of what the conditions of inflation were like in 10 to the minus 32 seconds after the Big Bang. That's an unfathomably short amount of time.
Absolutely.
And if we actually convincingly can, we'll make those measurements, and when I'm looking at that plot of what we call the power spectrum, and it reveals what the universe has to tell us, that's going to be just such an unbelievable moment.
Absolutely. And, before we head out, you have worn so many hats on this mission, but you have a hat here today that I just wanted the audience to see here. He brought a SPHEREx hat with him as well, and I just wanted everyone to be able to see your great gear that you truly wear many hats, including one of SPHEREx.
I'm literally wearing my SPHEREx hat.
Well, thank you so much today, Phil, for answering all our questions. And thank you so much to Emily and Jen for giving us a behind-the-scenes look at SPHEREx. We are now going to talk about where we can see the information that is going to come in if you want to learn more about the mission. So to do that, please visit nasa.gov/SPHEREx. And then you can also follow along on social media at NASA JPL, NASA Universe, and at NASA. And if you'd also like to take a look at the press kit and learn more about SPHEREx, use go.nasa.gov/SPHEREx press kit. Again, thank you everyone for your questions, and thank you so much for watching.